So now this video discusses about what we call as the bivariate data. So what is the bivariate data? So first thing, we need to understand what we call as the experimental unit. We need to understand what we call as the experimental unit. Now if we say experimental unit, that is the object or the system in which the data is obtained from. That is what we call as the experimental unit. And the data can be obtained from the body of an object. Let's say from the body of a person. Let's say the body temperature can be measured from the body of a person. That is experimental unit. The body of a person, that is the experimental unit. And for instance, let's say we can have to measure, let's say, the length of a leaf. The actual tree itself, that is the experimental unit. That's where the length of the leaf is measured from. And basically from the leaf, that is the experimental unit. So whichever the investigation you can have, where the data is being collected from, that is what we call as the experimental unit. The experimental unit can also be the community where the data is obtained from. Let's say if we are talking about the data that is in terms of, let's say, the number of households. So the households themselves, that is also part of the experimental unit. And from the perspective of the experimental unit, we have 2 or 3 types of data. We have what we call as the monomial data. So what do you think monomial data is? So monomial data, that's about the variable, single variable obtained from the single experiment unit. So that is the data obtained when the single variable is obtained from the single experiment unit. In other words, let's say we have the body of a patient. Now a doctor can think of measuring only body temperature. That is what we call as the monomial data. That is on a particular body, we just have to measure a single variable. So that is what we call as the monomial data. And we can also have, let's say, we just have to measure the blood pressure on the body of a person. That is a monomial data. In other words, on the single variable, actually on the single object or on the single experiment unit, we just have to measure a single variable. So that is what we obtain. It is to be monomial data. That is the data obtained. That is a single data obtained from the single experiment unit. And I also have what we call as the bivariate data. So that's the point of interest in the video, bivariate data. Now on the bivariate data, that's when we are measuring 2 variables on the single experiment unit, but these variables has to be actually related. So we'll be talking much about the bivariate data in this video. And I will also have what we call as the multivariate data. So now on the multivariate data, that's when now we are measuring we are measuring 3 or more variables from the single experimental unit. So here's the question for you. Try to have examples of monomial data and multivariate data that you should have understand. And I want to see the responses in the comment section below if you can have that one. So let's see what is the bivariate data as the lesson centered at. So if we say bivariate data, these are the 2 variables measured from the single experimental unit. But now these variables has to be related, whereby one has to be independent and the other one has to be dependent variable. And let's say from the body of a person, we can measure, let's say, a body temperature, and let's say we can measure body temperature versus, let's say, body temperature versus let's say rate of metabolic. So I should say metabolic rates. metabolic rate. Let's say body temperature versus metabolic rate. So mind you, metabolic rate, that's the rate in which the chemical reactions are taking place in the body. So basically, metabolic rate is the one that affects the body temperature. So when the metabolic rate increases, it means the body temperature also have to increase. So which means in this case, metabolic rate, that is independent variable. That is, we can call it as independent variable. Independent variable, and the body temperature has to be dependent variable. And also in the same case, independent variables are denoted as x, and where that of dependent are denoted by y. So that's about the bivariate data. That's where actually two variables are measured from the single experiment unit. And also try to come up with examples of bivariate data in your own cases that you should have to understand. And of course, you can also have, let's say, mass versus age. So mass and age. So mass and age. This is also bivariate data. So as the person is growing up, the mass tends to also increase as well. That is also bivariate data, in which the mass of an object or the person or any other living thing is depends on the age of that particular object or that particular living thing. Let's say, for example, if we talk of a person, as a person is growing, the mass itself also grows. So in that way, it means age itself, that is independent variable, where mass is said to be independent variable. So that's how you start to understand about the bivariate data. That's two variables measured from the single experiment unit, but these variables has to be actually related, whereby one has to be independent and the other one has to be dependent variable for that case. So keep that in mind. So ways of presenting bivariate data. So ways of presenting bivariate data. So what are the ways in which bivariate data can be presented? So ways of presenting bivariate data. Ways of presenting bivariate data. So how do you think bivariate data can be presented, if that is the so bivariate data can be presented using what you call as the scatter plot. You can also present that one, scatter plot. We can present the bivariate data, and I can also use what you call as the stacked bar chart. So stacked bar chart can also be used to present bivariate data, and I can also have to use side-by-side bar charts. You can also use this to present the bivariate data, side-by-side bar chart. You can also use this to present the data, and I can also even use the line graph as well to present the data. So line graph and any other sort of the graph that you may think about. And for the sake of interest, we would like to discuss about the scatter plot as one way of presenting bivariate data. That is for the sake of interest. But at your own time, you can go through the other ways of presenting data I've mentioned here. So a scatter plot, that is one of the ways in which the data is presented. That is bivariate data. Now, how should you have the scatter plot to present the bivariate data? And for the sake of interest, let's say we have the data. That is, let's say we have the bivariate data about the height versus weight. Let's say we have the height, and we have the weight. Let's say that is the case. We have the height, and for this case, what it means is that the heights represents the x values, and the weights represents actually y values. And for this case, we have the height, let's say 150, and let's say its corresponding weight is given as 45. And let's say we have 160, and its corresponding weight is given as, let's say, 50. And let's say we have 170, corresponding weight is given as, let's say, 55. So we have, let's say, 180, and let's say corresponding weight is given as 60. So let's think of coming up with a scatter approach and for this data. So with the pencil as well as the ruler, we need to come up with a scatter plot that we can have to present the data. And in the sense that we'll have it as this. Now in this case we'll have, this is we know that this is the y-axis, and this is the x-axis. You should have to understand. And we'll have to label x-axis is presented by the heights. So have the heights, that is, and the y-axis is presented by the weights. Let me just have to use W for the weight there. Should be presented by W. Let's say that is the case. And on the same case, let's see the scale that can be used along x-axis. Let's think of using, let's say, should be, this is the origin, we have it as well. Let's say we should have 50. Let's say we should have 100. We should have 150. Let's say we should have something about 200. That's the scale we can use. And along x-axis. And how about along y-axis? We can have, let's say, let's think of using 10. We have 20. We have 30. We have, let's say, 40. And we also have, let's say, something about 50. And let's say we have about 60. Let's say that is the case. So in this case, we'll have, let's start with the height 150. What is the weight corresponding to height 150? So we have height 150 and the weight is given as 50. So have it somewhere here. So we just have a star at that point. And we have the weight is 160. What is the height? We have it as a 50. By the way, and now for this case, we need to have this. By the way, with respect to 150, we have the weight which is given as 45. So 150 weight is given as 45. So it has to be somewhere here. So that's where we should have to be. And 160 we have it as 50. So 160. And that should be 160, and the weight is given as 50. So 160 should be somewhere here. That we can have it as weight given as actually it should be 50. That has to be somewhere about. That has to be here. And we have 170. And we have 170. It has to be somewhere at the center here, somewhere at the center. And what is the corresponding weight? We have it as 55. So which means 55 has to be, 55 has to be somewhere here. It should be somewhere there. So 170, 55, has to be somewhere there. Anyway, I'm not accurate, but in your case, you should have to be more accurate since you'll be using scale and the rule as well. Then you have 180. So 180 is corresponds to, there should be 60. So 180 somewhere here. So 180 somewhere and a 60 somewhere. So in this case, this is what we call as the scatter plot, where the points are indicated but without being connected. That is what we call as the scatter plot. So in some cases, the scatter plot may also look like this as a simple structure. We can have, scatter plot can also look like this. We can have a scatter plot, something like this. The where this corresponds to the x-axis and this is y-axis, and the points can be presented as this. And depending on the data, this can also be said to be the scatter plot, like that. And the scatter plot can also be something like this. You can also have the scatter plot, somewhere like this. And depending on the data, you can also have the scatter plot, somewhere like this. You can also have the scatter plot somewhere, like that. So keep that in mind. So that's how the scatter plot is actually drawn. And for the sake of perfection, you just have to practice more and more for you to be well conversant with the system of the scatter plot. But now, what is the information we can get from the scatter plot? Mind you, the variables has to be related either, directly. The variables has to be related directly. And if the variables are directly related, it means on the scatter plot we'll have the positive pattern. We'll have the positive pattern, and the positive pattern represents the positive relationship. So which means the variables are directly related in the sense that when one variable increases, other one is also increases as well. And we can have the indirect relationship. What is the indirect relationship? Now on the scatter plot, we can have the negative, should be negative pattern. On the scatter plot, we'll have the negative pattern. So on the negative pattern, it means when the one variable increases, other one decreases. So we'll have the negative pattern. So that is a negative pattern. And we can have no relationship. That is possible as well. No relationship. So no relationship occurs when the variables of interest are not related. So for that case, the pattern, the pattern is scattered. Basically, we do have the scattered pattern. So pattern that not really shows, or that you cannot define whether it is positive or negative. And what are these positive pattern, negative pattern, and the scattered pattern? Or should be, by the way, scattered pattern can also be said to be no pattern because the plots do not really shows what is the relationship, by the way. So we can have something like this. Now for this case, this is, let's say we have this case. Now this is what we call as the positive relationship, because the plots are showing the positive pattern. This is positive pattern. Where one variable increases, other one also increases as well. That is positive pattern. And I will also have what we call as the negative pattern. That is opposite of that one. that we can have it as, and for this case we can have this as a positive pattern. So we have this one as a positive pattern like that. And we have the null relationship, that is where the plots are not really showing the pattern, rather they're just being scattered. You can have something here, something here, something here, like that. So there's no relationship here. We cannot tell whether it is positive or negative. There's no relationship here. So this is what we call as the null relationship pattern, as you can see. So which means the scatter plot can really show how the two variables are actually related. So that's how you should have to understand that and up. And I try to come up with a scatter plot for the following data, so you should have to understand. Let's say we have the data given us. Let's say we have x, we have y. Let's say we have 2, 4, 8, let's say 10, 12, we have 10, 12, 15, 11, let's say 20. We should have the scatter plot for that data. And also try to come up with a scatter plot for the data below. Let's say if we have x, y, let's say we should have 2.5, 3.4, let's say 10.9, 15.5, and let's say y values should be given as 10, let's say 9.5, 8, let's say 4.9. So how should you have the scatter plot for that data? Like that. And now let's be talking about what we call as the correlation coefficient. Correlation coefficient, and which is symbolized as R. Now this is the numerical value that is also being used to describe how two variables are related. That is what we call as the correlation coefficient. It is the value symbolized as R that is being used also to describe how two variables are related, either directly, indirectly, or no relationship. That is what we call as the correlation coefficient, and it is described as the numerical measure of bivariate data. That is the correlation coefficient, and it is calculated as R is equal, AC subscript XY. This is said to be covariance, and divided by the standard deviation for X values and the standard deviation for the Y values, where covariance is calculated using the formula given as, the summation of, and that is xi minus should be y bar x bar, and the times yi minus y bar, and that is divided by n minus 1. So that is the formula for the covariance data. Should be covariance, and in some cases that can also be calculated as, summation of xi times yi, and that is minus, summation of xi, and that should be times the summation of yi, and divided by n, and overall, and where overall divided by, let me just have to squeeze this, where overall is divided by, where overall we divide that one by, and that should be n minus 1. So all these are the formulas for the covariance. And we can also have, and how about the standard deviation for X? So by the way, this is a sample standard deviation. Now X, which is the standard deviation for X, is calculated as square root of summation of xi minus x bar to the power 2 divided by n minus 1. And likewise, standard deviation for actual y will be calculated as in the same way. And that will be given as, s y is equal to the square root of, that is should be the summation of yi minus y bar to the power 2 divided by n minus 1. In other words, the formulas that we are using here are the same formulas we actually used on the measures of the dispersion. So that's the sample standard deviation you should have to get. So of which, whenever the value of r is negative, it means the variables are inversely related, that is indirectly related. And whenever the r is positive, it means there is a positive relationship. If r is 0, it means there's no relationship. So you should have to understand about that one. So let us see how we can have the value of the correction coefficient using the formula we have recently talked about. And of course, we also have another formula you should have to bear in mind. And basically, we have, by the way, I'll give it at the end of the video. You should have to get. And let's say we have the data below. Let's say we have the data that is being given as, let's say x, and we have y, which is given as 2, corresponding y value is given as 3, and we have 4, 5, let's say 6, 7, and let's say we have 8, and here we have 9, and let's say we have 10, and here we have 11. Now, how should you have to calculate the correlation coefficient for this data, if that is the case? So keep in mind about the formulas that are being used. We understand that the value of the correlation coefficient is calculated using the formula, covariance divided by the product of the standard deviations, and for x as well as the y, and of which covariance is calculated as, we have the summation of xi minus, let me just have to take it back properly here. We have xi minus x bar, and the times that one as yi minus y bar, like that, divided by n minus 1. And where these are the sample or standard deviations, and for the x as well as the y, that we'll have to do that one later. That I'll have to present that from actually those formulas later as well. So looking at the formula that we have, first thing we need to have the mean for x as well as the y values. So what is the mean for x? So mean for x is given as 6 upon calculating, and the mean for y is given as 7. Make sure you understand how to make use of your calculators properly in order to simply calculate the mean. So these are the values of the means you should have to understand. And also, as far as the formula is concerned, we need to come up with the following table. So we need to come up with the following columns of the table. And that is, we need to have the column for the means. So mean for x, mean for y. You also need to have, xi minus x bar somewhere, yi minus y bar somewhere. We just have to try to squeeze more, and that will accommodate. And what you have to understand is we need to for that case we need to have another column, that is the column for, we should have xi minus x bar square, and we'll have, let me just have to eliminate the column for means, otherwise we need enough space for this. We just need enough space for this, and basically we just have to we should have the another column for the yi minus y bar square, somewhere like that. And of course, for the sake of space, we also need, of course, another column for the product of another space. Let me just have to try to squeeze more here to accommodate some more actually columns. And in your case, you should be more accurate in your doings. And we should also have the another column for the xi minus x bar times yi minus y bar. At least that one is making sense, and that's the enough columns that we can have. And minus y bar, like that. So now what is happening is this. So for this case, we understand that the mean for x, is given as, should be the mean for x. Let me take it back. The mean for x is given as 6, and the mean for y is given as, should be 7. That's the information we have. Then let's just have to look at how we can have to operate all those things. And on the third case here, it means the x value actually minus the mean. So that is 2 minus 6. We have it as negative 4. And here we have y minus the mean for y, that is 3 minus 7. That is negative 4. Then here what it means is that we'll have the square of this column. That is negative 4 to the power 2, that is 16. And here we have negative 4 times, actually negative 4 to the power 2, that is 16 as well. And this column corresponds to have the product of this and that. That is negative 16 as well. Should be positive 16 rather. We should have it as that in that column. And in this case we have 4 minus the mean for x. That is 4 minus, should be 6. That is negative 2. We have negative 2. And we have 5 for y minus its mean. That is a negative 2 as well. So we have negative 2. And a negative 2 to the power 2, that is positive 4. And also here we have positive 4. And what is this times this? Now we can have it as, should be positive 4 as well. Then we have the another x value, which is 6. And now 6 minus the mean for x, that is 0. And 7 minus mean for our, actually for the y, that is 0 as well. Then we have 0 here, that should be given as 0, and also have 0 here as well. Then we have 8 minus the mean for x, that is should be positive 2. and 9 minus mean for y, that is 7, that is positive 2. And the square 2, we have it as 4, and also here we have 4. And the 2 times 2, that is also 4 as well. We have it as 4. And the 10 minus c should be a 6, that is given as 4. And 11 minus 7, that is given as 4 as well. Then 4 to the power 4, that is 16. We can have it as 16 here as well. And also we should have it as 16 here. So that's how you should have to understand that one. And from there, what you should have to understand is we should have the summation of this column. That is 16 plus 4, that is 20. And also we have it as 40, that is the summation of this column. And we should also have the summation of this column. That will be given as, by the way, we should have 4 here. And that is also, we should have it as a 40 for this column. And also we should have the summation of this column. That also being given as 40 as well. Like that. And that's how you should have to get it up. Now back to the formulas that we need to have. So we understand that what is the formula for the correlation coefficient. We said it is given as covariance, which is x should be s subscript xy divided by sx and sy. And for that case, we said sxy is given as, that is the summation of xi minus x bar times the times yi minus y bar divided by n minus 1. So what is this on top? Now this one corresponds to the summation of this column. That is now being given as, should be 40. And n corresponds to the number of paired values. That is 1, 2, 3, 4, 5. So which means n is given as 5 and minus 1 is given as 4. So have 4 here. So half divided by 4, that is given as 10. So which means the covariance is given as 10. And how about sx and actually sy for that case? So by the way, we're saying covariance is given as, let me put it here, is given as 10. And let's go for the standard deviation for the mean as well as the for the x as well as the y. Now the standard deviation for x will now be given as the square of summation of this column square. So that will be given as 40 divided by, that will be given as 40 divided by the total number of x values, that is 5. 5 minus 1, that is given as 4. Now have the square of 10. And how about for y? And also y in the same way, you have it as sy, that will be given as, for y we also have the 40. And divide by 4, that will be given as also 10 as well. So we have the square of 10. That will be given as that. So now for this case, we just have to substitute into the formula and be able to have that one as that. So in this case, the correlation coefficient will be given as r is equal to, we have covariance which is given as 10, and divided by the square of 10 times the square of 10. Now as you can see, what is the square of 10 times the square of 10? So you can see that in this case we'll have the covariance, actually we'll have the correlation coefficient, that will be given as 1, because we'll have square root of 10 times the square root of 10, that will be given as 10 as well. So since this is the positive, it means it is a positive relationship, and it is a very strong positive relationship that you should have to understand. So that's how the correlation coefficient is actually calculated in that way. And also try to have the value of the correlation coefficient for the data below. Let's say if we have the x and if we have y, that is, let's say 150, and the y is given as 45. And we have, let's say 160, and the y is given as 50. We have 170, and the y is given as 55. And we have 180, and the y is given as 60. So how do you think we can have to calculate the value of the correction coefficient if that is the case? And also try to have this one as well. Let's say if we can have something about, let's say, the data x, that is 2.94, 5.67, let's say 2 point should be 6, let's say 6 point, let's say 99, and let's say we should have about 8.64. Let's say that is the case, and the y values are given as, let's say 20.9, 30.9, 40.9, let's say 0.25, let's say 50.96. So we should have the correlation coefficient and for that data in that way. So that's how you start to understand about the correlation coefficient. So if the value of r is positive, it means that's the positive relationship. And if the value of I is negative, it means that's the negative relationship. And if it is out, it means there's no relationship. You should have to understand. So that's what you call it as the correlation coefficient.